This module introduces normal density curves. Here we are talking about a probability density curve or a probability distribution function. This is a curve that is meant to quickly visualize the relative histogram for some data set or some population. When you see the curve in your mind's eye, you should imagine a bunch of thin little bars that are being drawn that the curve is meant to approximate. For normal density curves, there are a number of key features that we can take advantage of. The first two items are true for normal density curves, but they are actually true for every probability density curve. First, a probability density curve is always above or on the x-axis. It just so happens that a normal density curve is strictly above the x-axis. It is always above the x-axis, though in many cases this would be hard to tell as it would be so extremely close to the x-axis you couldn't tell it wasn't actually on it. The second point, true for every PDF, is that the area under the curve between the x-axis must total to an area of 1. As we are going to associate area with probability, we can also say that the area is 100%. The next feature that is true for normal density curves that we will often take advantage of is that the curves are symmetric about the mean. So if we have a symmetric curve, which is just meant to represent the histogram, so if we have a symmetric histogram, this would mean that the shape of the heights of the bars below the mean would be the same as the shape of the heights of the bars above the mean. So that gives us some information about the median. Because of the symmetry, if we can flip the curve or histogram about the mean and get the same shape, this means that 50% of the bars must be below the mean and 50% of the bars must be above the mean, because they would land on top of each other when we flip them over the mean. Thus, the median equals the mean for any normal density curve. The next observation is that the normal density curve is unimodal. If the curve is unimodal, this would imply that there is only one mode, and that mode would have to be the mean. This is because if the mode was any value above the mean, it would have a symmetric counterpart below the mean, and this violates the fact that there is only one mode. So this means for a normal density curve, the three common measures of center are all the same. The median equals the mean, which equals the mode. Now, this fact is actually true for any bell-shaped curve, and we will see that not all bell-shaped curves are normal, but it is also true for a normal density curve. There is one additional feature that holds for all normal density curves, but I can only explain it at a conceptual level, because the full explanation requires the use of calculus. Some of you may have had calculus, and this concept will be familiar to you, but for those of you who have not, this won't be an issue for this explanation. The normal density curve has two inflection points. An inflection point is the part in the curve where the curve switches from being a right side up bowl to an upside down bowl. Notice how this part of the graph looks like a right side up bowl, which means it would hold water. But this part of the graph would not hold water, because if it were a bowl, it would be upside down. The inflection point is where the curve switches from being a right side up bowl to an upside down bowl. The reason this turns out to be important for a bell curve is because of the values where the inflection points are located. Let's draw a bell curve. We'll start with the part of the curve that looks like an upside down bowl. In this direction, the curve goes in the shape of a right side up bowl, but it levels off toward the axis and never comes back up to finish the shape of the bowl. So it is more like half of a bowl in shape. The same thing happens on the other side, but going in the other direction. Because of the symmetry, this is the mean, the median, and the mode. This is the center of the entire curve. Now it turns out that if you go the distance from the center to the first inflection point, that distance is the standard deviation of the distribution. By symmetry, it is the same if you go to the inflection point to the left or to the right. The distance from the mean to the inflection points is one standard deviation. Said another way, the distance between the inflection points is two standard deviations. This is somewhat convenient if we want to make a quick sketch of a normal density curve. You can estimate the standard deviation location by approximating the place where the curve transitions from being an upside down bowl to a right side up bowl. This is meant to have been a quick introduction to normal density curves. Now we are going to focus our attention on a special normal density curve, the standard normal density curve. This refers to any curve that has a normal distribution with a mean of 0 and a standard deviation of 1. Any normal distribution with these two attributes is called a standard normal density curve, which is also called a standard normal distribution, often abbreviated SND. SNDs prove to be very useful throughout all of statistics because they allow us to compare any one normal distribution to any other normal distribution. In an earlier lab activity, we talked about the set of thermometers. The readings of these thermometers had the nice feature that the mean readings were 0 degrees Celsius and the standard deviation of the readings were 1 degree Celsius. Because the distribution of the readings was normal, this means that the readings of the thermometers followed a standard normal distribution. You may recall that there was an added degree of complexity in the thermometer activity because there was a discrete unit of 0.2 degrees. So when you looked at any one thermometer, you could tell if it was 0 degrees or 0.2 degrees, but you couldn't distinguish a temperature more refined or more precise than that when looking at this type of thermometer. Now, you could imagine a thermometer which is more precise or possibly to any degree of precision. In fact, this was one of the issues you had to wrestle with when going from the cumulative frequency table, where everything was reported in those discrete units, to trying to approximate what you would expect from a normal distribution, which is continuous and can take on any value to any degree of precision. As a precursor of things to come, we will see that if you are given any normal distribution, or normally distributed data set, you can convert that data set to z-scores. This can be done by transforming every value x in the original data set to its z-score, the distance of that value x from the mean measured at standard deviations. Once you have done this, you have two data sets, the original data set and the z-score data set. For this new data set, the z-score data set, the mean is 0 and the standard deviation is 1. But we're going to put this on hold for now, and we will return to this shortly. For now, we will focus only on a distribution that looks like this, normally distributed with a mean of 0 and a standard deviation of 1, i.e. a standard normal distribution, an SND. This will be somewhat of an abstract discussion of this distribution, but we may occasionally refer back to the thermometer example as a concrete setting in which to better understand the concepts. With the standard normal distribution, we are going to introduce a special function in Excel. The function we will talk about is the NORMSDIST function. This function is the cumulative density function for the standard normal distribution. Let's start with the curve for the standard normal distribution. We know that the center of this curve would be the mean, which is z equals 0. If you go to any value on this curve, say z sub 0, there is some area under the curve bounded by the x-axis to the left of this value. The function NORMSDIST is the function that gives us this area. Mathematically, we would write it this way. It is the probability of obtaining a z-score that is less than or equal to our value of interest, z sub 0. In our mathematical notation, we'll use a capital Z to refer to the random variable, and we'll refer to the value of interest as z sub 0. So z sub 0 is what we would enter into this Excel function. Let's work an example problem with this new function. The function returns the area to the left, so we will start with a problem asking for the area to the left. Here is our problem. With a standard normal distribution, an SND, what is the probability of randomly selecting a z-score of -1 or less? Mathematically, the way we would write that would look like this. P of z less than or equal to -1. This is asking for the probability that z would be less than or equal to -1. The Excel function will give us this result straight away. We enter NORMSDIST, and I will stress that the S is indeed important here as there is another function in Excel called NORMDIST, and the S here emphasizes the fact we are talking about a standard normal distribution. We enter equals NORMSDIST -1. When we punch this in Excel, we get back the value 0.1587. The interpretation is that there is about a 15.87% chance of getting a z-score of 1 or less. Let's look at this graphically. This graph shows us the area under the SND to the left of the value -1. Visually, it seems reasonable that we are seeing 15.87% of the total area under the curve shaded here in purple. If we were to think of this as a relative histogram, and there were lots of thin bars under the curve, the bars that would be shaded here would amount to 15.87% of the total data. Question: What is the probability of getting a z-score greater than 1? Well, because of the symmetry of the curve, 1 and -1 are both the same distance from the mean, but on opposite sides. So the area to the right of z equals 1 would be the same as the area to the left of z equals -1. In other words, the probability of a z-score of 1 or larger would be 15.87%. Alternatively, if I want the area to the right, I can use the rule of complements from probability. The Excel function NORMSDIST gives the area to the left, so if I take 1 minus the value from the function, that will give me the area to the right. Using the symmetry of the SND, we have the relationship that the area to the left of z is 1 less than the area to the left of -z. In the syntax of the Excel formula, that would be NORMSDIST of z is the same as 1 minus NORMSDIST of -1 times z. Now let's return our attention back to the area of the unshaded region between these two shaded regions. If the two shaded regions are each 15.87%, if we take 100% and subtract 15.87% twice, or subtract 31.74%, we would get 68.26%. Now let's stop and think for a moment. Z-scores are just standard deviations, so if we want to know what percent of the information falls within one standard deviation above and below the mean, well, what does the empirical rule say that should be? The count by thirds empirical rule says this should be about 70%. The traditional rule says 68%. And as an approximation, most people would agree that 68.3% could be approximated as 70%. So what we are seeing is that the empirical rule isn't too far off, as long as we are talking about a normal distribution. Now let's focus on a problem attending to the area to the right of a given value. We just did a problem focusing on the area to the left. Our new problem focuses on the area to the right. We are still working with a standard normal distribution. What is the probability of randomly selecting a z-score of positive 2 or more? Mathematically, that is asking the probability of 2 or greater. Recall, the functions in Excel all give the area to the left, so if we want the area to the right, we need to take advantage of the fact that the total area is 100%. So we would enter 1 minus NORMSDIST 2. Or we alternatively could enter NORMSDIST -2 because of the symmetry of the standard normal distribution. This gives the result 0.0228 or 2.28%. Let's take a look at the graphical representation of this on the normal density curve. Here's what we just calculated. The shaded area here represents 2.28% of the total area under the curve. This would be 1 minus NORMSDIST of 2, because NORMSDIST would give the unshaded area to the left, and with the total area being 100%, or 1, we have our desired shaded area to the right. Again, we can also take advantage of the fact that this is a mirror of the area on the other side of this symmetric curve. The left shaded region is the area to the left of z equals -2. Thus, we could just enter NORMSDIST of -2. Thus, we have a couple of ways we can obtain our desired value. Now, let's calculate the remaining unshaded area in this picture. If there is 2.28% for the area in each tail, this is a total of 4.56% in the shaded regions. Subtracting this from 100% gives the unshaded area as 95.44%. Again, let's assess how this compares to the empirical rule estimate of 95%. As approximations go, 95% would not just be a good approximation, but the result if we were actually rounding to a whole percentage point.